Okay, here is the lesson on the bridges. Experiment 1, cantilevers. I've shown what happens in another video showing actually the setup. However, what I'm going to do now is just talk through sort of the predictions and how we're going to work this experiment. So, first of all, predictions. What we're talking about is we're looking at how the load is increased and therefore what happens to, and I'm going to exaggerate this, the sag, how much it's deflected by. And what we're going to look at here is the prediction, and I'm pretty sure that if we were to draw some axes, axes are already there, sorry. So I'd say as we increase the load, then the sag increases. In actual fact, I think it's, and now that's qualitative. However, if we want to be quantitative, put numbers to it, I think if we double the load, then we double the sag. What does that mean in terms of a graph? Well, if we have the sag against the load, that means it's a nice straight line that's going through the origin. Okay then, so write down all the factors you think could affect the sag. Well, of course there's a load. That's the one we're going to be using, hopefully. We also have the span, how far the supports are apart, the material as well, and I think that's probably about it, because those are possible independent variables of which my dependent is the sag. So in this experiment, which of these variables are going to test to see whether we want the load? What must you do to keep them constant? Hence, control variables. How many values in the independent will you test? What range will these be? That's a really good point. In actual fact, in the actual experiment, we were dealing with something like 0 Newton. Of course, 0. We start with 0. That's an important point. Up to about 8 newtons. In other words, we're going from 0 grams up to 800 grams. And then the type of material used, what affects that, what type of material cannot be described with a number, like load. What would you just, what type of variables? Right, so it's categoric. A little bit like eye colour is, it's either wood or a different type of wood, but you can't put a continuous line of materials like you would get a continuous line of load. So we've done there. So it's categoric. And how would you plot it? Well, often you would do it with a bar chart. Something like that, a bar chart. Excellent, okay. Now, with that in mind, we've seen all of this on the other video, and if not, you can go and have a look at the video. It's given all the results. And then you've drawn a graph, and you've said how one behaves the other. See the other video for all of that on the link below. How is the analysis of the results? Now, we're going to do this quite a long-winded way in order to show you how to analyse results nice and accurately. So, here's an example of a table of results, x and y. It's very mathematical, the way we're approaching it to start with. 4, 10, 8, 4. What happens here is that it's directly proportional. As I said before, if you double one of them, then the other doubles by the same proportion. Good. Here's another list of values here. 2 to 5, 4 to 10, 8 to 20, 12 to... So that means that if let's say I double this, then you notice that's doubled. Whereas if I've quadrupled that one, you notice that this one has quadrupled, and so on. So why is it that when y equals 2, x equals 2, y equals 5? Well, that's because for every one value of x equals 2.5 values of y. That's the relationship we're dealing with. So 1 to 2.5. So therefore, when we're looking at this table at the bottom here, 2 to 5, 4 to 5, what is y divided by x? Well, 5 over 2 is going to be 2.5. 10 over 4 is going to be 2.5, 2.5, 2.5. There's the same ratio between the two. Another way of showing that it's directly proportional. So this value that we found, 2.5, is that value k, that constant of proportionality. In other words, we could rewrite this equation as y equals kx, if you like. Y equals kx. So with that in mind, what's going to be the relationship here? Well, 1 is going to be 2.5. 3 lots. Maybe I should write this, make it slightly easier. 3 lots will be 7.5, 5, 12.5, 15, 17.5, and we go on, 27.5. So this is showing this relationship. The numbers here are showing that there is a direct proportionality between x and y, and the constant proportionality is 2.5, or k. So let's see what happens with our actual loads themselves. So if we look at the values that we have, just need to find the values that we have. It says that from our results, 1 Newton gave us, and you can see the results on the table linked at the bottom of the video. So we'll just find them nice and quickly. You will see that with 1 Newton, the load is 11 millimeters. Okay, 11 millimeters. So if we were to double the load, then we'd expect 22 millimeters, sorry. However, from my results, if you look them up from yours as well, we find something like 27.5. So are they directly proportional? Well, sort of. Bear in mind, the smaller the sag, the more the error. What is the difference? The difference is about 5 millimeters, and over 20, that gives us 20% error. That's quite a lot. However, let's not become despondent. Let's see what happens here. Let's look at when we have 0.5, we had a 6.5 millimeter, sag. When the load 2.5, 34.5. Does this look directly proportional? Well, 2.5 to 0.5 is a multiplication of 5. So therefore 6.5, if we multiplied that by 5, we should get 32.5. We actually have 34.5, so that's not bad. I would say, with all the experimental error taking place, that I would say is directly proportional. Bear in mind, we've now got it slightly larger sag, so therefore there will be less error. Okay, then let's look at the graph. Is it? Well, you'll see from the results that the sag versus the load does pretty much go through the origin and is a straight line. You'll always get some little variations going on here because there are some errors in your measurements, but yes, it is. Remember, straight line through the origin equals directly proportional. Okay, and finally, what we have here is, we have by calculation. Let me just write down, I've taken this straight from the table of results. We have 6.5 for 0.5 newtons, 11, 19.5, 27.5, 34.5, and 43. So what is that? So what's this asking for? What's that k value? That constant proportionality, if that is of course x and that is y, what is k? It's going to be y divided by x, just like we did before. We've just changed the terms. If that is the case, well, 0 divided by 0 gives you impossibilities. 13 here, 11, 13, 13.75, it's looking similar, 13.8, and 14.3. So, do they look approximately constant? Well, I'd say yes. And you're not going to get them identical. This isn't a mathematical exercise, it's a physics exercise. I mean, other than the 11 and the 14, it's about 13-ish. So if the constant of proportionality is the same, then coming back to here, then you can say that the constant proportionality is the same, then it's directly proportional. Constant proportionality is the same, it's directly proportional. Are there anomalous results? Well, yes. At 1 Newton and 3 newtons, I think they look a bit dodgy. You've used 3 methods. Which one do you think is most effective? Well, they all have their strengths, but I think the graph is easiest to see. And, you know, when people look at the numbers here, they go, oh, that's not exactly that, so therefore it's not directly proportional. So in your mind, you have to say, well, actually, the difference there is very minimal. However, from a graph, you instantly see the fact that it is you instantly see how far the values are, and therefore how light. Yeah, I'll draw it. You're instantly going to see how far the values are off, and whether it looks like it should be directly proportional or not. Okay, excellent. So just remember when you're going through this, use your results, of course, unless you haven't got them. And if you don't have them, then the results are kept on the video below. Okay, hope that makes sense.